it going, guys? Good? Yeah, me too. All right. Okay, glad to see I didn't make a typo on my title screen as well. Just what I emailed you guys. Okay, so my project's about estimating mineral surface area to apply to critical load calculations in a region with high acid deposition, Kitimat, British Columbia. Okay, so first let's chat a little bit about Kitimat. So it's located, I think it's like a 15-hour drive north of Vancouver. It's cheating a little bit because you got to zigzag around the mountains there. It's in the coastal western hemlock ecozone. Mountain and ocean influences make it one of the wettest climates in Canada. The dominant soils in the region are ferrohumic podzols, and the soils are wet and cold over most of the year, meaning that they have a high organic matter content, low pH, and low base saturation. I did some sampling there at the end of November. I can confirm that it is both cold and wet. It's also home to some very grizzly men and some very grizzly bears. It's crazy. It's like 60% males in Kitimat there. So if you go into the local pool hall, see plenty of these guys. The men, not the bears. I don't think they're that advanced. It's also one of the most beautiful places I've ever seen. Yeah, so it's pretty cool. Okay, so the reason that this town came to be was this company called Rio Tinto. They've changed their name like 40 times now, but this is the one that they're sticking with right now. So there's a big aluminum smelter in Kitimat, and it recently went in a modernization plan. They changed their VSS smelting technology with a pre-bake AP40 smelter. So I don't need to explain to you guys what that means, right? So essentially they're just converting to a more modern smelter. The smelter that they're changing to is used around the world and is considered sort of the standard now. So it works great for everyone. Aluminum production goes up by 49%. Polyaromatic hydrocarbons are decreased by 97%. Greenhouse gases go down by 57%, and fluorides by 37%. So everything's sounding great, except the sulfur dioxide emissions increase from 27 tons a day to 42 tons a day. So sulfur dioxide is really acidic, and this can affect a lot of different ecosystems. So what they needed to do, Rio Tinto needed to apply for a permit to change their emissions plan. So here we have the current limit at 27 tons, and they set the upper limit at 42. So a study was done when they applied for this permit to change their emissions plan, and they took into consideration soils, water, air, wildlife, and people, I guess, into consideration, and they gave it the go-ahead. They gave it the green light to go through and increase their emissions. So, and on your guys right there, that's the plume from the smelter. So the red zone at the bottom there, that's right where the smelter is, just off the Douglas Channel there, and right in the city of Kitimat. Okay, acid deposition and critical load. So we know that the smelter is going to be kicking off a lot more sulfur dioxide, which is really acidic. And we know that increases in acid deposition from anthropogenic sources can lead to harmful effects on ecosystems. The maximum deposition that an area can take before we see these kinds of effects is known as a critical load. So because we know this, we've come up with this conclusion that too much acid, not good for ecosystems. It's also not good for people either. We didn't get to interview this guy about this experience. Okay, so my particular area of interest is forest soils. So I want to see the effect of acid deposition on them. So the way that acid affects forest soils is we know that they deplete plant nutrients such as calcium and magnesium. We also know that they can increase the mobility of inorganic carbon, which can damage tree roots and affect the ecosystem. So this picture is from Sudbury, which, as I'm sure most of you know, was an area that was really devastated by an increase in acid deposition, and the forests end up looking something like this. So it is a big problem. We're getting better at dealing with it, but it's something that's still prevalent. Okay, so we know that critical loads are what we need to calculate to determine how much acid that we can spit off. So how do we go about solving these? We use something called the simple mass balance model. It looks pretty simple. It actually is. We can cut it down pretty nicely. So in the area that we're working in, we're only worried about sulfur. So we're focusing on this second equation here. And so as we go through, we're looking at as we're looking at base cation deposition, we're gonna go and try to imagine a worst case scenario. So we want to if things are as bad as they possibly can be and there's no base cation deposition, we want to see how the ecosystem is going to do without that. So we're going to go ahead and assume that the base cation deposition is 0. The chlorine deposition, it's actually too far from the sea to get any of that, so that's also 0. And base cation uptake we can calculate by, so the base cations get uptaken by forestry efforts, so we can go through the forestry logs and calculate that. And then the acid neutralizing capacity, this big beautiful equation here, which you can see is all a bunch of variables that we already talked about. So we're going to focus on this bad boy right here, base cation weathering. What's base cation weathering? I have a slide for that. So base cation weathering, also known as mineral weathering, is the main contributor to acid neutralizing capacity for soils. So so as it works, as the acid is coming down, the soils can actually break down and produce positive anions to then buffer the negative anions coming in. So that's the main way that soils can buffer incoming acidity. So that's what we're going to focus on when we're looking at our critical load calculations, is this base cation or mineral weathering. So now within mineral weathering, there are a bunch of different factors that contribute to that. However, we're going to look specifically at mineral surface area. So the way that we calculate the weathering is using a model called profile. And profile is kind of the gold standard when it comes to mineral weathering models. So we want to figure out what affects profile the most. And that is surface area. So over here is a sensitivity analysis. So what they did was, these are all a bunch of different minerals, the different lines. So they changed the surface area, and it had a dramatic impact on the weathering rate. So we know that surface area is the most important thing to calculating weathering rate, and we know that weathering rate is important to calculating acid deposition. This is an input page full of profile, or for a profile. There's a bunch of different variables. Anyway, I'm going to go on. Okay, so I've been, talking about a lot of stuff. So just to kind of break it down, so we talked about acid deposition, which is measured by the maximum amount of acid deposition that an area can take is measured as a critical load. An important factor to determining critical loads is mineral weathering rates, and the most important thing to determining mineral weather rates is mineral surface area. So that's kind of where I come in. Okay, how do we measure mineral surface area? So we use a tool called the BET, the Brunauer, Emmett, and Teller, because they like their name so much they decided to name the thing after them. So they use gas absorption to measure the surface area of the soil. Essentially what we do is we put the soil in a tube, blast it with nitrogen, and all the nitrogen that sticks, that's what we assume is the surface area. However, this process takes a really freaking long time and is really expensive. So for me to do 15 sites, it takes about a month for me to do that. So not only is this process really long, but we need to prepare the samples in order to do that. So how we prepare the samples is, so when you put the soil into the BET, if you don't do anything to it, it's going to measure the surface area of the organic matter and not the minerals, and not the mineral soil, which is not what we want. Organic matter has a really high surface area and doesn't really affect mineral weathering rate. So what we need to do is we need to remove all the organic matter from the soils. So to do that, we run it through something that we call a sodium hypochlorite treatment. I do a bunch of stuff and get all the organic matter off. It's really effective. We know that it takes essentially all the organic matter off, but it takes a really long time. And I can only smell chlorine for the next couple of weeks, so it's really, maybe not the best. But yeah, so it takes a really long time to do that. Okay, so in order to get around doing these treatments and then measuring it in the BET, some studies develop these functions, which are called pitot transfer functions, in order to estimate the surface area, so we don't actually have to measure it, we just estimate it. So these guys, these are two Swedish guys, Sverdrup and Furfinger. They came up with this idea. So they use these variables, sand, silt, clay, which are really easy to measure, to then estimate the surface area of the soil. So we just everyone wants to save some time doing all this stuff. So, but there's also a Scottish group, Hodgson et al. They tested this particular equation on some Scottish soils and found that it really didn't work very well. And then there was a Canadian group, actually from Trent. They did some studies out in Alberta. So what they did was they applied the two equations that the Swedish guys came up with and found that it really didn't work very well for the Alberta soils that they used. And they also used the Scottish equation here, and it also didn't work very well for the Alberta soils. Then they made their own equation, only using sand, silt, and clay. And they found it worked a bit better, but still not very great. So these models, when you take them out of the area that they were developed for, they don't travel very well. Similar to Guinness and crying babies. Yeah. Okay, but both the Scottish guys and the Canadian guys, I feel like maybe starting some kind of war here. Both of them found that when they include other factors, not just sand, silt, and clay, they found that they were able to get a better fit. So again, this is the Alberta guys. This is their model. Once they included factors such as up there, they still have clay and silt, but they also used a bunch of the mineralogy from the area in order to get a better, in order to get their model to be a better fit. Okay, so my project. So it's broken down into 3 objectives. First off, I want to see if the sodium hypochlorite treatments are 1, necessary because they take forever, and 2, if I do them and if Eric does them, we want to make sure that they're repeatable. We want to make sure, because it takes about 2 weeks to do these treatments, there's so much that can go wrong. If we can't even generate the same numbers from time to time, then there's not really any point. So that's the first one. The second one are determine factors that are related to surface area. And the third one is develop a function similar to what those guys did that we can apply to the area that is being affected by the modernization project. Okay? I mean, it makes sense to me, but I've been doing this for a while. Okay, so first off, we got to choose some sites. So so there was the initial project that they did back in 2012 before the permits were applied. They had 81 different sites, all within the area of the plume. So we still have all that soil at Trent. So it was great for me. I got to take most of the soils from there. However, I still wanted to go up in a helicopter. So we went to some additional sites. Up in that area as well. So I have 32 different sites out of the 81 there that I'm going to be working with. So here's the town of Kitimat down here, and the smelter is right up the Douglas Channel. There's the mighty metropolis of Terrace up there. It's got an airport. Oh, okay. So yeah, when you're working in the field, you need a lot of great help, but you also need to have a great time. I was going to ask him for his permission for this picture, but he doesn't work here anymore. So this is one of the field assistants working with us. But this is also pretty cool. So here's him augering down in the soil. I'm going to step out so everyone can see me. So augers are about this tall, but we couldn't get to mineral soil in this area because we're in the frickin' rainforest, and there's dead trees and moss that are sometimes too deep for a meter of an auger to get to. So anyway, I just thought that was pretty cool, and that's him swinging on a giant bear. Also cool, different reasons, I guess. Okay, so again, objective 1 of my project, is the treatment of soils prior to analysis necessary, and if so, is it repeatable? So what I did here was I took a site, and I took the soils from the site, and I treated it, and I measured the surface area on that, and then I didn't treat it, I measured the surface area on that, and that's what you get with the blue dots here. So ideally, we'd like these to fall along the 1-to-1 line, saying that they'd be the same. Well, not ideally, but if they were to be the same, they'd fall along the 1-to-1 line. And then what I did is I used a method called LOI, which is another method of removing organic matter. I put it in a big furnace, turned up to like 450 degrees Celsius, and let the suckers burn. So neither of these work very well. We want every single time there's still organic matter present, and we're getting a higher surface area on those. So it goes to show that the sodium hypochlorite treatment, we need to do that. So now, is it repeatable? So what I did was I did some. I took 3 different sites. I treated them all once. I got Eric to treat them all once, and then one of them I did for a 3rd time, just for kicks, and then I compared them to each other. So once again, we'd like to see them falling along this 1-to-1 line if they're repeatable, because we should be able to get the same thing or about the same thing every single time if this is repeatable. So here I have the averages and then the largest and smallest number. So after running some statistics on this, I found it was pretty repeatable. All three of these sites, no matter what time I did it, we got relatively the same answer. So we know that we need to do the treatment. We know it's repeatable. Leads us to objective 2. Determine factors that are related to surface area. So some of the factors that I'm going to be looking at are organic matter content, which is going to be measured using LOI, particle size analysis, that's the clay silt sand that we talked about, mineralogy, elevation, bulk density, soil moisture. So this is kind of what I got. So these are all to determine things that are going to be hopefully put into my model in order to predict surface area. So we can see something like bulk density really doesn't work very well. And then I have the three most reoccurring minerals. Plagioglass, which is really great. Apparently that predicts about 75% of the things that are going on there. Hornblende, not so much, and neither potassium feldspar. And then the other ones, so percent clay, which we were expecting to be the best predictor, was okay. And then the other ones, I don't think that we can really use too much. But we'll see. So then objective 3 was to then develop an equation using these things that are much more readily available than surface area in order to get a better way to estimate surface area. So first I wanted to compare, if I used the original transfer function, just using the sand silt clay, and applied it to my site that I've modeled, you can see at a low surface area, it's pretty tightly around the 1-to-1 line, but as soon as the surface area gets high, the model loses track of that, which is pretty similar to what everyone else has found so far. So I haven't gotten around to developing this model yet, so that's next on the plate. And also, so once I develop the model, I'll be able to take the readily available information from all the sites that they use for the KMP and be able to apply the model to that to measure weathering rates, then measure critical loads. I've also got this side project I've been working on. Would a potato be a better president than Donald Trump? That's still so good looking. anyway, so we'll see. The data hasn't come back on that. I don't know if I need to develop a model for that one though. Okay, so once again, is the treatment of soils prior to analysis necessary, and is it repeatable? So far I found that yeah, they're definitely necessary, pretty repeatable. Determine factors that are related to surface area. I'll probably be focusing in on clay as well as the mineral plagioglass. Those seem to be the best predictors so far. And I'm going to use that to develop this model that I can then apply to the greater Kitimat area. So why does this matter? So in order to, we want to be able to get a better understanding of relationships to surface area and more readily available information. The other studies that have been done on this are focused in Scotland and Sweden. Ours is in the rainforest out west. And also increasing the accuracy on the surface area estimates means that we're increasing the accuracy on critical loads. And also that Rio Tinto Alcan well, I guess Rio Tinto is sticking around for a while, and also LNG is moving into town, so whenever we're looking at emission management plans, having a readily available pedo transfer function will save a lot of time and money on estimating surface area. Special thanks to my supervisor Sean, committee members Julian, Kathy, Colin, field assistants Kevin, Phaedra, Connor, Chris, Emily, and my friends in the lab, Eric and Liam. Thanks for listening.
There's a really thick layer of organic matter before you get down to the mineral soils. Does that mean that that could impede buffering? Like in a real world situation, if the mineral soils are really low in the soil sample, does that mean that you're going to get acidification of the surface and it's not actually going to travel down to the minerals?
Maybe out of the gates, but it'll get down there eventually.
But would you get like a gradient of acidification in the soil kind of thing?
Okay, yeah. So one of the parts that I also didn't include was I did look at how surface area varies with depth, and I found it wasn't significant, and so I didn't put that in there. So it wouldn't affect the models in the long run. But when you're looking at weathering rate models to apply to acid deposition, what they do is you take 3 different depths of the soil, and then you blend those 3 different depths together using bulk density as an indicator of kind of how much soil is in each layer. So, like if 0 to 10 centimeters, for example, is not actually that compact versus the 15 to 30, that's how you blend them together. So it could have some effect, like the lower layers are most likely going to be acidified later, but we're assuming that it's going to get down there at some point.
How does soil permeability, the permeableness of the soil, affect the results too? Because I'm kind of curious about that.
Yeah, absolutely. So bulk density is a way of measuring the permeability of the soil. Okay. So that's one of the ones that we applied. So we normally it's used pretty among most of these things. It's something that's used used a lot. However, when I was applying it to the numbers I looked at, the R value was like 0.04 or something like that. It seemed to have essentially no effect on the surface area. Yeah.
Is that because of the type of soil in the area? Is it all virtually 30% type of soil, or is it?
It could be. So the way that when I was selecting my sites, I tried to split it up between as many different bedrock categories as possible. But because essentially all of them are in the rainforest, when they're not in the rainforest, they're on the beach. The words of the great Jay-Z, the beach is better. Then, that was a bad joke. What was your question again?
Well, I guess so in that case, there is a difference though with soil type. Though,
Absolutely, absolutely. Yeah, that could have an impact as well. And so mostly in that, we're looking, so the key things to look at there would be the mineralogy of the soil, as well as how all the other factors contribute, and those together make up the characteristics of, regardless what type of soil it is, those characteristics should answer that question.
Marcus Morginova on the background. That maximum capacity for the area that this company was given the air permit for, how do you measure that? How close it is? Does it make the ecosystem around that area more fragile if you actually achieve that value?
If they hit the 42 tons a day that they're saying is their maximum value?
Yeah.
So what they did was they did a report that involved studies done on soil, water, air, wildlife, and human health. And all 5 of those factors, if any of them came up with anything damning against that, then the project would have been shut down. But they found, all 5 of them found that it would have little to no impact on any of the mediums that we were looking at. Yeah. So I can't speak too much to the other ones, but I know for the soil. For the soil one, they gave it 3 different codes. Green is there's not going to be any impact. Yellow is we might see something, so we're going to keep an eye on it. And then red meant that they were going to shut it down. So for soil, they gave it a yellow. So what we've done is we've set up these long-term monitoring sites. So there'll be consultants going back every single year and checking on how things are going and going from there.
Does it make a difference whether or not they're doing this work for the next 10 years or 20 years or 50 or 60? Like at a certain point, does what's okay now become not okay anymore? And do they test regularly?
Absolutely. Yeah, so there is a group based out in Kitimat that's made up of a bunch of different people. So there's consultants involved there, as well as the First Nations group in the area, and Rio Tinto has their own scientists that are involved in it as well. So they go back we've set up these long-term monitoring plots, and they'll be going back every year to keep checking in on how things are going.
This might just indicate that I don't know much about trees. But it was my impression that evergreen trees tend to prefer acidic soils. So are there adaptations that these forest species already have that would mean that acidification would really impact them?
So you're right. So you're right. They do prefer acidic soils. The problem is when they become too acidic, they can't adapt fast enough to anthropogenic effects. In the case of acid deposition, so you're right. They will. The trees themselves probably have stuff to deal with it. We're also finding the soils in the area are used to a high income of acidity, so they also are prepared to deal with it. That's why this change in anthropogenic deposition doesn't seem to be harming the trees or the soil. So that's definitely something that has to do with it. But we just want to make sure it doesn't get too acidic. There's always a baseline.